Hello everyone, welcome to my Physics 1 Lab 2 presentation. So in today's lab, we explored the motion of a falling object and the forces on an object while explaining terminal velocity on a falling object. The two key fundamental principles of interest for today's lab was drag force and gravitational force. We used two computational models, one with only gravity and one with gravity and drag. The main result of our experiment was that the computational model with the drag represented the object better than the model without the drag. Here are some of the key physics principles used, and it includes Newton's second law, which is the net force on an object equals the change in momentum over the change in time, the updated velocity formula, which calculates final velocity of an object, position update formula, which calculates the new position of an object, drag force formula, as well as the gravitational force. Here are our observed model definitions. Our surroundings were the air, our system was our paper ball, and in tracker we needed to find the position versus time graph of the paper ball. Our key assumptions is that gravity and drag are the only forces acting on the system. The ball of paper has an initial velocity of 0 meters per second as it starts at rest, as well as all the tracker markings are at the center of the object. This is our experiment and tracker analysis. As you can see, I plotted the tracker points on the center of the paper ball, and it resulted in these graphs. Here we have the graph of the three combined trajectories. So the blue line is the trajectory of the drag, and the light green line is the trajectory of the object from the analysis in the video experimental data. And then the dark green line is the trajectory of the object predicted by the computational model, which is the gravity only. Here is the computational model that the code produced. On the left-hand side, we have the initial conditions that were set for our code inside of VLab. Here are additional coding details for the while loop. We have the code that symbolizes how net force was calculated, as well as how the drag force was calculated and how the proportionality constant was set. Some similarities versus differences. The similarities were that all the datasets showed upward motion followed by downward motion consistent with gravity. The shapes of the trajectories were also qualitatively parabolic. Some differences is that the experimental trajectory fluctuates due to hand motion and random noise. The gravity-only model predicts slightly higher peaks than experimental, since drag slows the object. The gravity plus drag model predicts lower final y values, which is unphysically below the floor, indicated numerical error or wrong parameters. Some possible sources of error include unsteady hand motion, the camera angle, timing errors, as well as environmental factors like the AC. What does this mean? Terminal velocity is when the net force on a falling object is 0, i.e. the gravitational force equals drag force, so acceleration is 0 and velocity is constant. The gravity-only model does not predict terminal velocity. However, the gravity plus drag model theoretically can predict terminal velocity, but it does not stabilize before the paper ball hits the floor. A similar experiment would be to drop the object from a tall height so it has enough time to reach at a constant speed. A new experiment that can be done is an object being thrown straight up with the same speed. If the vertical motion determines the total flight time, then the initial speed magnitude is the same. The time straight up equals the time to go up plus the time to fall down, which is longer than the time along a diagonal trajectory. When thrown straight up, it is greater than the vertical component of an angled throw, which will lead to a longer flight time.